I'm Matt Godbolt.
And I'm Ben Rady.
And this is Two's Complement, a programming podcast.
Hi, Ben.
Hi, Matt.
How are you doing?
I'm doing pretty well.
We've just had a moment of exasperation, haven't we?
Yeah, we're probably talking over the intro. Probably not at this point, but maybe earlier.
Maybe earlier. I don't know. I'll fix it in post as I always try to do, or increasingly less. In fact, I try. I think I've kidded myself that the charm is all about like the fact that a dog's barking in the background and there are children screaming across the road and we and lip smack and other things. It's kind of ASMR actually, isn't it? No, yeah, ASMR. So recently there's been a lot of talk about the Dutch manufacturing company that makes the lithographic systems for chip manufacture, and they're called ASML. And I just can't help but get the two things mixed up. They're very different things. But that's not what we came here to talk about today, is it?
It's not. I have an idea. I have an idea. Okay. I have a thing.
Tell me about your thing. Whoa.
Let's say, careful now. Let's say for the sake of argument, I have a program. Stop it, phone.
There we are. More charm. More charm has just entered the room. His phone, Ben's phone, unmuted phone.
I have a program and I want it to run fast. How would I do that?
Oh, wow. That is a great question. And we only have around about 30 minutes, 40 minutes to talk about it. So I've got a feeling.
So immediately this is going to be our first 10-part series.
Maybe so. I don't know. This is one of those questions because I think obviously deliberately you have asked me a leading and vague question. Because what do you mean by, in fact, each of those words, right?
Can you please define each of the words that you just used in that sentence?
Right.
Yes,
my program, make my program fast.
Right.
So, okay, I think we can cause it to become my program. You have something that you wish to go fast. Right. So the only word we really need to define then is fast. And I'm pretty sure you don't mean stopping eating for a period of time.
Right. Well, I think you could also define my program because in this hypothetical thing, I haven't written anything yet. Right. It's like I want to write a program. Doesn't exist. But I want the execution of that program to be fast.
Fast again.
For some definition of fast that we will define shortly.
Right. And so, yes, not no eating, not also unmoving, which is the weird other case of stuck fast, which is like one of those really
weird, the opposite of this
auto oxymoronic words, like inflammable or something like that.
Right.
You mean to go quickly. All right. So let's talk about what that could mean. Right.
Yes.
So the instant you say that, and because of what we've been doing professionally for a long time, and for what I've been doing most of my career, I think of low latency is fast. Like if you decide you need to do a thing, if your program needs to do a thing and it discovers that need, it should act upon it as quickly as possible, having discovered that need. That is what I mean by sort of low latency. It reacts to a real-time thing as quickly as possible. And I think a lot of embedded systems work in this world. A lot of UI, in fact, is this, right? If you said, hey, I want my, responsiveness in a UI is about latency, right? But that's one form of fast. But there's a very real, very important other kind of fast, which is I'm writing a distributed message passing system. I'm Mastodon, right? And I'm dealing with an enormous volume of information. And if I was slow at doing that, eventually I would back up, and I would never keep up with the current world. It doesn't matter. Individual messages may take a few seconds to go through if that's not fast. I mean, maybe that is fast for that scale of network, right? But you're talking about a throughput problem, or bank clearing is another one. They've kind of got a bit of latency. You beep your card when you're at the coffee shop, and it goes beep, and you've got like waiting 6 or 7 seconds, and that's a completely fine human amount of time. It's an eternity for computers. But on the other hand, there are several 100 million people in that same 5 second period tapping their card on their reader in the
Right.
same time.
Right.
And so there's a lot of things to go. So those things. So we've got latency and throughput. And are there any other um, aspects?
I think for the definition of this conversation, I think latency and throughput are two dimensions of fast which we should consider.
Okay.
I think you could maybe come up with some other ones, but again, we have 30 minutes.
Well, I mean, again, we can make this into more, but so
That's true.
do you want to? Which one do you want to start with?
I think we should start with latency.
Okay. So then we get into this sort of amazing set of questions that we get into when we're dealing with computers, because how fast is fast now, right? How quick is um like we just said, if I'm a human waiting at a sales kiosk, if it takes me 30 seconds to pay for something, that is not fast. If it takes me 3 seconds, it's probably okay. If it takes 0.3 seconds, I won't notice that that anything happened, really. There's a beep and I'm out of there. And any other order of magnitude less than that, like 0.03 seconds or whatever, is immaterial to me at that point, and it doesn't matter. But you and I work in a world where at least some of the things that we have done or are adjacent to, we are talking about maybe 7 or 8 orders of magnitude faster than those 3 seconds. We're talking hundreds of nanoseconds, hundreds of microseconds. And I have to remind myself that a nanosecond is a billionth of a second, right? You know, sometimes we throw these words around. I mean, maybe this is just, again, you and I and the weird world that we live in, but like nanoseconds are kind of a completely normal measurement for a 3 gigahertz computer. A few clock cycles is a few nanoseconds. That's completely normal. Yeah, that's reasonable. And then like to good old Grace Hopper's light foot. A nanosecond is here's a foot of copper wire. That's a nanosecond. You're like, oh shucks, man. That's the speed of light. It's the fastest thing that there is. Can only go a couple of feet in the time it takes me to add two 64-bit numbers together. That is insane, frankly.
It is insane. I whenever I think about that, I just think about Grace's wire just twisted around on the inside of the CPU and all the places where it would need to go in order for the light to move in that way to add those two numbers, and it just makes my brain melt.
Yeah, it is quite something. And the fact that we've taken these Factorio factories and we've crushed them down into the size of my thumbnail, and somehow snaking around in there are many, 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 many hundreds of feet of cable. The as you say, in each individual electron is, well, they don't go all the way down. It's complicated, right? Let's stop pretending that we can talk about that as well. So we've got many orders of magnitude here. So we could break it down into things that need to be measured in nanoseconds, in microseconds, in milliseconds, and seconds. And that's I think probably after that. I think the latency of something. Maybe you still can measure it in minutes, right? I mean, let's think about publishing a video on YouTube. Right, I've just updated my video on YouTube and I click the button to publish it, and it takes how many minutes to transcode it to all the different formats that YouTube does before it becomes visible. Maybe that is measured in minutes, and maybe I do care about that latency. But I think the thing that I can confidently talk about, and maybe you as well, is the sub-second orders of magnitude of latency. So let's talk about what can you do in that amount of time.
Right.
What that's a good starting point of not only if you say I would like my program to be fast, without even knowing what your program is, I've got some bounds on what you could reasonably expect to do in hundreds of nanoseconds, hundreds of microseconds, hundreds of milliseconds, right?
Right.
On commodity hardware, if we're just talking about things like a regular PC or a regular, a decent server in a data center somewhere, or a laptop or something like that, they're all within spitting distance of each other.
So if we think of latency as sort of like the time between an input is provided and an output is produced.
Sounds
then
good.
Automatically down in the tens of nanoseconds range, you're sort of like, what output could you possibly consume, or what input could you possibly consume, and what output could you possibly produce in that span of time, right? Because it's got to go into the computer and then come out. So maybe a theoretical example here would be like a robotics application where you have some active control of a system or a set of servos or something like that, where you're trying to like imagine like the robotic dogs type thing, where you're just like taking like some information from like the sensor on a robot and then feeding it back and using that to adjust. Like that's already going to be up probably in the like low milliseconds range, probably. I mean, I don't know. I'm not an
I'm not
expert in
sure either.
robotics, but
No, but I mean, you think about things that do like autobahn or drones, like
yeah,
a self
yeah,
that can't be milliseconds because it's already upside down by the time a
yeah,
millisecond of wind has caught it, right?
yeah,
So
yeah, yeah,
they
yeah.
must be a little faster than that. But maybe we're talking microseconds at that level. It seems not totally unreasonable to have some sensor update and put something on a bus internal to a system on a chip kind of thing that can then
Mm-hmm.
go, oh, wait a second, I need to speed up this rotor a little
Mm-hmm.
bit more to
Mm-hmm.
account for that. Right.
Yeah, because a
But
lot of
you're
those times
absolutely
those
right.
outputs can be sort of like targets, right? So they don't. It's not necessarily that it needs to go like all the way out to like a servo or something. It's just kind of like, okay, I've gotten this input, and now I need to adjust, my targeted angle here, right? And there's maybe even some other external system that is like actually making the adjustments to the physical objects, but like you might want that target to update on the order of tens of mics or hundreds of mics,
Right.
just because when you do, you get sort of like a smoother, more better prediction of like where the arm needs to be or something like that.
Right. And
Yeah.
yeah, so I mean, let's to sort of break it down to sort of consumer hardware. It is difficult to get a message in and out of a computer in you know, I mean, like you just do a ping, right? You ping a
Hmm.
local network, a computer on your network,
Yeah.
and it's less than a millisecond, but it's still hundreds and hundreds of microseconds probably to go through commodity hardware. And for the kind of weird stuff that you and I have been involved with, there is some very specialist hardware that happens, which we can't really talk about, on the far end into the nanosecond range of things. So I suppose if we're
Hmm.
talking about things that most folks could reasonably put their fingers on a keyboard and program, be it a little embedded system like an Arduino or
Hmm.
an ARM type thing, or indeed a program like I'm typing on a computer and I'm expecting when having pressed a key press to see the key appear in the terminal, that kind of thing.
Hmm.
We've kind of picked now our range. Now we're talking probably hundreds of mics to low millis.
Hmm. Hmm. Yeah. Okay. So
So
I've got a program.
yeah,
It's
so we're
gonna
down. Yeah, that's right. I forgot where we were now.
it's gonna
You have
read some input delivered from outside the computer, and this is a commodity computer,
yep,
like,
yeah,
and then it's gonna produce some output that is also going to leave the computer, right? And we're thinking that this is going to have to occur. It's going to take at least hundreds of mics for that to occur. Is that
I
is
think
that a
so.
fair statement? So that's like
Without
the upper
getting
bound of how fast we can make it for my definition of
with
fast.
I think so. I mean, there are exotic techniques and things that you can even use on commodity hardware that is a little bit more exotic, like DPDK, which is a sort of network bypass thing with you can fiddle with, and if you put a second network card in your computer, you can go faster. But yeah, I think
Mm-hmm.
let's say already whatever you're doing, if you're responding to an external network event,
Yeah.
you're doing any kind of reaction to it and sending it back out again. We're in the microsecond region,
Yeah.
but probably hundreds of microsecond region would be my instinct. And maybe
Yeah.
I'm wrong. Maybe I've forgotten how computers are these days,
No one
or at
knows how
least like
computers actually
normal
work.
computers, right? Normal computers.
Yeah.
I mean, actually, I was telling you before we started recording, I'm surrounded with networking gear and computers and things and AI agents running things for me as I'm setting up. I'm actually upgrading my home network to like 2.5 gig because that's actually
Mm-hmm.
something that is not totally unaffordable for the home these days now.
Mm-hmm.
So I'm like,
Mm-hmm.
hey, maybe my ideas about what commodity hardware is out of date, but
Yeah.
um,
So my first question would be, when I'm writing my program, how do I make sure? Because my assumption here is that the input here is unpredictable. It's not like you're going to start the program and immediately be provided the input. The program is
mhm,
running.
yeah,
There's something outside of the computer that creates this input, and then the program has to react and create an output, right? So
yeah.
my first question to you is, how do I make sure that there's the minimum possible latency between the generation of that signal and the code in my program running?
Well,
Something
that's
something ePol, right?
no, exactly right. No, well, yes, and no. I mean, that goes into the DPDK sort of thing I alluded to. So,
Hmm.
yeah, a traditional server program that is maybe blocked on a socket. So you've got a socket, you've got, let's say UDP, just to make things maybe easier. I don't know, right?
Mm-hmm.
You've got a blocking call to receive, which means that your process has gone to sleep, told the operating system, hey, anything interesting coming in on this port, this UDP port, I'd like to know, please. And then I've gone to sleep and I've been descheduled. And now I've just been chucked in the list of all the things that are currently, all the processes that are currently asleep and have nothing to do. So that's where we are now. Packet comes in, goes through the standard kernel process of saying, well, who's this for? It's port 9007. That is registered to this process. So we're going to write it into a buffer now rather than discard it, or rather, we'll keep it probably around in a buffer that exists. First of all, is there space in that buffer? Yes, there is. Okay, this is something you configure for each socket, how much space that you can have, which gets complicated if you're sharing multiple processes listening on the same. It's yeah. Anyway, and then we go, well, who cares about this, right? We've put it into the buffer now. We've copied the data. Who cares? Oh, there's a process. Okay, well, this process is waiting on this, so we should mark it as ready. This process is now ready to be scheduled, and then you're done. And then, as part of the whole you're done process, the kernel goes back to, well, I guess I'm now finished, but back to the user process. Now, who should be run? And maybe there was something else that was going on that CPU when the packet came in, and that other process is actually still higher priority in whatever queuing fairness there is. In which case, it will merrily do whatever it was doing before until it runs out of the time slice that it had allocated it, and then it goes, oh, someone else's go now. Oh, look, this thing's ready. So what I'm sort of getting at here is there is a lot of things that happen between that packet arriving in your kernel and your process being woken up to do anything about it, and that's a
Mm-hmm.
hugely
Mm-hmm.
variable amount of work too. And you can definitely reduce the amount of work, the amount of other things that the CPU or the kernel is trying to do on a CPU, so that your process is more likely to be woken up. There are schedulers that let you set these things as priorities and stuff. But the way that I intuitively do these type of things is using some kind of like we said, DPDK, which is this sort of networking layer that lets you use shared memory with the network card. And then instead of the kernel being involved at all, you just continuously read a place in memory that the network card will write directly to and say, hey, I've got a packet for you. And then you just pick it up. And then essentially your latency goes down to how fast a PCIe bus transaction can notify that a piece of memory has changed, and you pick it up and off you go, right? But that is still fairly esoteric. So it seems like that's not a fair thing. But I guess it's the difference between, right, if the program part that we've not even started talking about now
Mm-hmm.
is itself going to take tens of milliseconds because of the innate amount of work that it has to do, and so the upper bound is dominated by its processing time, then maybe the effort and all the work to put in shaving tens of microseconds off on the like the interrupt handling
Mm-hmm.
time
Mm-hmm.
isn't worth it, right?
Mm-hmm.
It's a lot of engineering effort, it's a lot of complexity, it's a lot of non-standard nonsense. But if we wanted to make something go as fast as possible, those are the kind of things that I would take to doing, is to take the kernel out of the equation and burn a CPU core just spinning, doing nothing other than saying, is there anything to do? How about now? How about now? How about now? In a tight loop, and potentially reschedule everything else so they can't run on the same CPU as me. There are ways that you can do this with CPU sets, with isolation trickery, kernel isol CPUs in a kernel command. There's a lot of weird things you can do. Anyway, right. And then you can get it down to, in the limit, single digit microseconds between a packet arriving and you going, okay, I have work to do.
Mm-hmm. Okay. So if we assume that the work that needs to be done is relatively simple, right? You're going to do some adds, you're going to do some multiplies, you're going to try to structure your code so that you're really only doing adds and multiplies, and then you're going to produce some output that is purely a function of that input and whatever state
All
you
right.
may
So
have held in memory.
what we've got is an ALU as a service. We are. Have you seen? There's a guy who's written a micro services based CPU emulator where every single instruction is handled by a different microservice, each of which is written in a different language, and the thing
Oh
runs, and
my
it's so.
God, that's
But yeah,
amazing.
isn't it cool? I love that people think of these things.
Man, you think you were in microservice hell? You should.
Yeah, you've got like literally 256 different
Oh, that's
things, and a
amazing.
RAM memory service so that everyone can agree on this. It's cool. But so you're talking about something like that. Let's just say,
Yeah.
it is. In fact, honestly, probably a decent, unless you want to. I'm going to say these, and you can tell me if where you're trying to steer it is right or not. But like
Yeah. Right.
something like a Redis memory cache is like one of these things. It's like something
Sure.
comes in, I look it up in RAM, and I'm like, yes, I've got it. Here it is. It's like a small piece of data, a key value store that
Yeah.
is just like a cache, right? You're not
Yeah.
doing very much work. It's not as banal as like I'm adding the three numbers you've given to me and
Right.
giving them back to you. It is. You can imagine there is actual value in that, but it's still
Yeah.
you
I'm
know
trying to draw a line about the other parts of the computer that you're going to be talking to. And what I'm trying to
I
say
see.
by this is that you can't ignore memory, right? It's
Yep.
not simply a function of the data that you've read in, but you
So
don't have to go beyond that, right?
okay, so let's use like an in-memory cache, like a Redis
Yeah.
is like without the disk backing type
Right.
stuff.
Right.
Yeah,
Hmm.
that's perfect. Okay, um, so yeah, you're looking. I mean, at that point, there's a without going into the extremely fun and interesting rabbit hole of how you actually do the lookup and what data structures you use, but that is
Hmm.
probably
Hmm.
the key thing is that like you must consider the data structures you use. But the interesting thing is that with a latency lens, you're not looking at data structures in quite the same way as you do when you're uh, doing like CS, whatever. I don't know what
Hmm.
numbers they use, but when you're doing
Right.
your data structures courses and you're
Yeah.
like looking at big O notation,
Right.
like
Right.
big O of n whatever n log n for your so like a not unreasonable data structure for a a key value store is something like a balanced red black tree, right? It's O log n log n to
Hmm.
look into it,
Hmm.
whatever. Another one is a B tree or a B plus tree or one of those kind of trees. Hash maps are other ones as well.
Hmm.
And obviously hash maps do have in theory O of one. So
Hmm.
you'd probably want to pick that out of big O notation or whatever. Um, but the other ones seem reasonable as well. Like it's like, but the dominating factor with something as straightforward as the thing you've just described, where we're literally just looking something in a key value store, is going to be reading from RAM.
Right.
Now, if you're talking about something that's so small it fits into L1, L2, or L3, which are in the order of tens of Ks in the L1 case, up to several megabytes at L3, and bigger than that on bigger servers and whatnot. But like we're still
Hmm.
talking like not all that much information.
Can you describe for our listeners? He said, covering for his own ignorance, what L1, L2, and L3 actually are.
Oh, I'm so sorry. So there are layers of caches. Caches are expensive and both in terms of their the amount of space they take up on a chip and how fast. Going back to our Grace Hopper,
Hmm.
the bigger something is, the longer it takes to get to the other side of it.
Hmm.
So the way that CPUs prevent us from having to read from the very slow RAM, which we'll talk about in a second, is that we have on chip caches and they are layered so that you have a very small, incredibly fast level one cache, which is usually not very large, tens of kilobytes kind of area. Then you have a layer two cache, which is maybe a meg, maybe a hundreds of K, that kind of area, and then a layer three cache, which is maybe tens of megs, maybe even a little more than that. And each of them is slightly further away, like literally physically. They're still on the actual thumb size chip inside the machine. They're further away, but it takes longer to look through them to find the data.
Hmm.
And so um, if you can fit something in L1, it's kind of almost free. I'm going to put air quotes over this. We're talking somewhere in the region of 5 or 6 cycles to read from RAM, and that includes all of the other things that are like the fixed cost of reading from RAM includes doing the lookup for the logical address that you've decided to read from, and then turning it into the actual physical address that it needs to go to the correct chip. Different different processes think that address 2000 has different data in it, right? And
Yeah,
something has to do that translation. And that's not at this scale, when we're talking about, a 3 gigahertz machine, a third of a nanosecond is a clock cycle. It's that lookup itself takes time.
Right.
And so,
Right.
we need to be doing some of that. So that's about the limit of it. And there's some other really complicated things that the poor memory system has to do, because of the weird out of order engine. But we'll ignore that for now. So 5 or 6 cycles for like an L1. And now I'm going to forget this off the top of my head. I really should have brought this up beforehand, but like tens of cycles, low tens of cycles for L2, maybe late tens, 80, 90 cycles, maybe L3. No, I don't think it's that much now. Someone, order of magnitude things. It's, still, probably only tens of nanoseconds, but then you go out to RAM and it can be hundreds of nanoseconds if you actually need to go out to RAM. So those are the layers. The other thing that's interesting is that usually on chips, the L1 and maybe the L2 are unique to the CPU core that you're running on. So
Right.
you just get a copy of your own, and then that's yours, and no one can do anything with it, with a massive asterisk and footnote for older CPUs, but we maybe won't go there. And then the L3 typically is shared amongst the other cores that are physically on the same chip as you.
Okay.
And so there are some contentions, and there are obviously conversations that have to happen between the chips to say, hey, I'm reading that. Oh, I was just writing to it. Oh, okay, well, we need to make sure that we do this in the right order. So there's a little bit more complexity there. But yeah, so if we're still talking in single, measurable, human countable numbers of cycles, keeping it inside the L1 or L2 is great. L3 is okay. And if we have to go to RAM, we have to be a bit careful about things. And at that point, two things are important to note about the way caches work. One is that the sort of the whole theory behind a cache is that having read a byte of memory, it's really, really likely you're going to read the bytes that are around that byte of memory. So the fundamental unit of work from the memory system on the CPU to the caches and beyond is a sequence of bytes, which is usually 64 or maybe 128 bytes long. And that's kind of like the atom that gets shipped back and forth. And some chips even do things where you say, well, you asked for this block of 64 bytes, I'll just get the next one and maybe the one after that while we're going, because we might as well, having just done that. And so this sort of temporal usage pattern is incredibly important for latency, because if you're following a linked list, as you may be if you just have a naive hash map, suddenly you're jumping randomly around in memory and the poor system can't make a guess. But if you just have a damn array of everything and just go, well, it's expensive, it's an order n operation for me to search through these things, but I'm going to run through them linearly, suddenly it may be more worthwhile from a cache standpoint, especially if a cache miss is hundreds of cycles. I can do a lot of work in 100 cycles on an out of order execution machine that has 12 execution units, right? So why don't I just do tons of work and hope that that's quicker than going to RAM? So anyway, popping the stack all the way back, to keep the latency as low as possible, you're going to have to think about this. And so you might want to make some concessions where the distribution of your latencies needs to be taken into account. Now, if you're going to say like, well, most of the time, I think I'm going to be this like 80% of the stuff we're reading is hot, like it's going to be commonly used again. In which case, I'm going to use a data structure which is fine. And that 80% fits inside. It doesn't matter what I'm doing, whether it's a balanced tree or whatever. It fits inside L3, let's say. But the 20% that's outside of it is just outside. It's going to be RAM. We're just going to have to take the hit every time. And the fact that it's incredibly expensive because we're using a balanced tree. So I guess now we turn around and say, like, it's not just how fast to go. It's like, what is the shape of your distribution? Is it better to have the average case fast and the bad case awful?
Right.
Or is it better to bound the bad case and say, well, actually, I'm going to use a linear search every single time. And I'm going to say that even the fast one where the linear search, it would have been faster just to check, I don't know, the first one or pack them in a different way. But, I'm paying the cost to do 16 compares every time and just go, well, that costs me a little bit more than one. Of course it does. But it makes the worst case go away, but the lowest. So yeah, sorry, I've just gibbered around in a big, as I've sort of like realized the enormity of the question you've asked.
that was the intention of the question. But yes, whenever you're talking about latency, you need to it's not like, oh, it's 10 microseconds of latency. It's 10 microseconds of latency in what case, what percentage of the time.
Yeah.
Oftentimes you talk about like P95, P99, P99.999 numbers of like what percentage of the responses are going to be less than some particular target time. And you may have multiple layers of that, right? Like you may have a maximum threshold that you need and like a P99.99, and then like a P95, and then like a median, right? And you might want to like structure things, differently based on whatever those targets might be. So in our case, sort of this hypothetical, robot dog type plugged into a PC, perhaps, that's receiving the signal. Maybe what we'd want to say here, as one fork of the tree to go down, is actually the thing that I care about is the worst case latency, right? I want because if the latency gets too high, the dog's going to fall over, and that will be bad, right?
It's a very common thing for like control boards and things, and this is why in those situations, typically embedded systems who have that kind of very strong requirements will use not regular operating systems. They use real-time operating systems that can give you hard deadlines for things happening within a certain amount of time, and or do no preemption at all. So there's not like a case that your process will have its CPU time taken away from it. It's like, it's your responsibility to keep running until you get to the end and then yield to the next guy so that you can. But this is a huge problem. As computers have gotten more complicated, it becomes harder and harder to reason about what an upper bound could be. Picking up my 6502 in its box over here.
Right. It's a little easier.
It's a little easier. It's like I can tell you exactly how long any single thing is going to take all the time. It's completely deterministic and it's well documented.
Right.
But we have to reverse engineer what the hell an Intel chip is doing in order to understand sort of maybe what the worst case is in that particular situation, right? Hey, what happens if we are trying, we have an L3 cache miss at the same time as another CPU core, like a physically distant core has an L3 cache. They both go for it at the same time. How does that work? Is there some really weird edge case where, in the fabric, it times out after some amount of time? I don't know, but and it's hard to find out. But if I need to give you an actual, like, someone will get run over if the brakes do not come on when I put my on the brake, then maybe I certainly can't think about the world the same way, but I certainly can't use certain like CPUs and designs and operating systems like that. So that's
So if I come to you and I'm asking you this question of how do I make this program fast, and you go through all of these follow-up questions, and what it turns out that I'm asking for here is how do I make sure that the round trip latency of this program that I have running on a just regular commodity PC is not going to ever be higher than 10 microseconds? The answer is you can't.
I think that's a fair. Yeah, the nearest people I can think of that have to deal with that specific problem are people who make digital audio workstations for consumer PCs, because they have a genuine latency bound, because if you're playing a keyboard there's a 1 second delay, that's not between you're pressing the button and hearing the noise change. That is not good for anybody. And so the only way that you can get that is to make everything as low latency as possible. But if you go too far and you don't have enough buffering between you and the set of audio that's coming out, then if you, for whatever reason, can't keep up, you're going to get a massive pop or a crack or a click as suddenly you have to catch up and just drop a whole bunch of samples that you were generating. So that's I don't know how they do it, honestly. In fact, I do know people who have worked on them, and we should perhaps consider getting them on to talk about this kind of stuff, because it's a fascinating problem. But anyway, but back to your
so the result of this, you can't. So
or
now
it's really,
like, okay,
really hard.
Right. It's like you're putting constraints on this problem that you can't really solve for. For example, you'd probably be better off using some specialized hardware rather than trying to do this on a commodity machine if you truly have a constraint that, of let's just say 10 microseconds
This
or
is
something like
to an
that.
extent. I mean, obviously, microcontrollers have been around longer than computers because they've been in things, or that's the original design. But that is why the brake disc controller in my car is not controlled by the one PC that is
Right.
like running the AV display in the middle
Yes.
panel, right? It is like
Right.
a very specialist piece of software running on a very specialist operating system, which probably isn't an operating system by anyone else's definition of operating system.
Right.
It's just a library you link against and then sets up the interrupt vector and hands you a few niceties and says, good luck.
Yeah. Yeah.
But that's why it's doing nothing but monitoring the disk, because then finally you can potentially say, all right, we can upper bound this stuff. We do know what the maximum latency could be. And it is, and I can sit and work it out on paper because it's an ARM. This is an in order ARM, and it only has an L1 cache. And even if it's whatever, there are things that you can say about it, and you can bound it that way.
Okay, so we've got our inputs. Maybe we've had some discussions about our constraints here, and we're like, all right, well, we can't do this to a maximum level of 10 microseconds. That's insane. We could maybe do something where our like P95 is 100.
Let's
maybe
let's
less
just
than
say.
that,
I mean,
more than that. Let's
you
do
and I
something
could
like that. Yeah,
we're making this up as we go along.
Yeah, and then our maximum is something much more reasonable, like a second, right?
Okay.
It's like all right, it's never going to take more than a second. If it does, then we have a bug and we should fix it, right? As opposed to, that's how the system works, right? So now we've gotten our message from the outside world. We've gone and looked up the value that we've cached. Hopefully that's an L1 cache, and hopefully we've done some smart things to make sure that it's there. But, again, this is why we have these ranges of latency. How do we write out the response? Do we have the same sort of operating system packet issue when we're trying to write this thing back out?
I mean, yes. If we're talking about standard, like, I mean, we keep changing what it is we're doing. Is it a dog that's falling over? Is it a UDP packet going into it again? But like, if we're going to send a packet back out again, then yes, there's a similar dance on the way out through a traditional operating system where you write to a bit of memory that you can read and write in user space, and then you say, "Hey, send it, please." And the kernel goes, "Well, I need to send it. I can't hand this bit of memory to the network card because this bit of memory is just wherever you decided to put it. It's maybe on the stack, whatever." And certainly the DMA engine for your network card does not have carte blanche to read any piece of memory anywhere in the whole system for all the obvious reasons of like separation of concerns, if and to do with some of the ways that they work internally. So the kernel has to copy it somewhere else in a buffer where it knows it could hand the address of that to a network card. And then it potentially returns back to you and says, yes, it's sent, even though it isn't. It's sat in a buffer. Time will pass. Eventually, the kernel will decide to schedule sending it. I mean, probably it will actually send it immediately, all things considered, unless the network card's already busy doing something else. There's these, and then the network card will be notified through some mechanism, and that's relatively expensive and requires a ping across the network. Sorry, I say a network. It is a network. The PCIe bus itself, or however so your network card is plugged into your computer, is effectively yet another network, and there's another hop, and there are complicated things going on there. So a message is addressed to it. The network card goes, "Oh, you say you have a packet for me. How quaint, how lovely. Okay, I'll go and get the address from the ring buffer. Here it is. Okay, and I'll start streaming it out." And so that process can be relatively latent too. And so again, you're less likely to suffer from the scheduling randomness that the kernel does, because it's not like something asynchronous happened and now the kernel has to pick you being amongst all the things that the next to do. It's like, you've given it a piece of work and it's very obvious what it should be doing with that work. But there still is some redundant copying of data. There is still some messaging to an asynchronous process, which is the network card itself. The network card can be like, yes, sure, fine. And then it could be busy doing something for all we know, right? I don't know what magic network cards are doing. Maybe it's, a virtual network card that doesn't even exist as a physical thing. And then really it's pretending to be a network card, but in fact it is in a data center on a shared piece of infrastructure, and what you're really doing is talking to the hypervisor, which then goes, "Oh, cool, a packet from one of my many
Hypervised.
virtual machines."
Yeah,
hypervised children, right?
So I'm kind of I was maybe teeing this up a little bit, but this is like somebody comes along and says, "Hey Ben, you made this program to control this robot, and you did it in a very silly way. Why are you using a UDP network? That is not necessary. Are there other devices that one could use? I mean, like a USB-C connection or something else that would be available to, just a regular consumer commercial computer."
Yeah, that's it. I don't know too much about the ins and outs of how the kernel interacts with the USB. I know that the underlying USB protocol and the thing you talk with the hub or whoever you're talking to on the end of it is sort of a negotiated thing. You can you negotiate bandwidth, you negotiate. I don't think you negotiate latency. I think you can negotiate isochronous, that is repeating things. So like if you've got a webcam plugged in, it can book, hey, I need to send this much data just all the time. And you get sort of time on the USB bus to be able to send packets over that data. But I don't know about like latency. And obviously things like, USB keyboards and things are nice. And gamers obviously use USB mice and whatever, but we're still talking almost human levels of latency there. Millisecond, sub millisecond, I'm sure. So I don't really know. The best guess I would be able to have is not to say something like USB, because again, there are sort of layers of indirection between you and the actual device, even if you're talking the USB protocol through the kernel somehow. But if you had like either GPIO on which is general purpose IO pins on one of the more microcontroller-y type systems, where you can literally just say, if I write to this memory address, it's not really a memory address. It is whatever data I put there is the highs and lows of these 8 pins, right? And at that point, you're like, you're off to the races, right? Or say a serial interface, which although serial is incredibly slow and awful, it is also something where you're kind of directly attached to, and you can say like, I'm just driving it myself. Now, I'm sure that's no longer true. Now I say it out loud, I'm sure that it's virtualized through some mechanism in the kernel, and so it's no longer the case if you open dev tty 0 that like if you get the okay, you are the only person talking to that now. And still, it would suffer from like if you read from it, then you would block, and the kernel will put you to sleep until a byte came in. So even that doesn't make sense. So GPIO is the nearest thing we have to the sit in a tight loop and wait kind of approach that we were talking about before. For both input and output, you could say like, hey, I'm doing a quiz show. Whoever presses the button first, kind of thing. And there are 8 buttons, and they go into the 8 bits inside my my controller, and I just sit in a tight loop reading from it. Obviously, there are better hardware ways of doing that, right? But I'm just sort of thinking out loud. Yeah, I don't know. What did you have an idea? You've been driving this in a direction, and I'm wondering if you have a solution in mind that I have not got to.
No.
I mean, by the way, have I got the job, or is it?
Well, you pass to the next round, but I'm going to have to.
We'll have to see. I mean, we're now 14 minutes in, so it's now. Do I not have questions for you? We've done far too many interviews, haven't we?
Yeah. No, I mean, I think that, we made the full kind of round trip, and I think that's good. I think the other, and if there is a part 2 to this, I think the part 2 should be, okay, now what happens when it's the actual like calculation that is the part that needs to quote unquote go fast, right? Like the IO no longer dominates as it did in this example. And it's basically just this exercise. And how do you take this signal, make sure that you don't accidentally make it slow when it's being processed in the CPU?
That's an interesting one. Yeah.
Okay, this is going to take a material amount of time, and we're trying to make it as fast as we can.
Yeah, which is probably what most folks think of when you say, can I make my code go fast, is the code part, not all the other stuff around the outside, but often that can dominate. Yeah, no, that would be an interesting one. So yeah, okay, we'll and then we've got to talk about throughput at some point, and maybe that will leg into throughput, because I think there is part of it, but we'll see. Well, all right, we rather mysteriously then, and now you and I have to look each other in the eye and go, we will remember that the next episode we record will be the continuation of this one. And we won't just leave our poor audience hanging.
Right.
So I apologize in advance if we do, in fact. But I think this has been very interesting.
Yeah, that's
hopefully
good.
Our listener agrees, and I will see you next time, my friend.
Next time.
You've been listening to Two's Complement, a programming podcast by Ben Rady and Matt Godbolt. Find the show transcript and notes at www.twoscomplement.org. Contact us on Mastodon. We are at twoscomplement@hachyderm.io. Our theme music is by Inverse Phase. Find out more at inversephase.com.